In this video, I'm going to introduce a few ideas related to discrete time signals in the time domain. If you've previously had a course on signals and systems, you'll be familiar with many of these concepts in the continuous time setting. I'll start with a definition of a signal. And there's a lot of ways you could define a signal, but we're going to start with something very simple, and that is that a signal is something that conveys information, and that information is conveyed in patterns of variation in that signal. We'll look at a lot of examples coming up, but for right now, I want you to think about a signal as something that conveys information through the patterns of variation in the waveform. We could also define it formally as a mathematical function that maps a collection of independent variables in the domain to a set of dependent variables in the range. Some examples that we'll look at here are, the first one is a sound wave or maybe a radio signal. Here you have a single independent variable, time, and then one dependent variable. Another example would be a stereo sound file or sound signal where you have two signals. Maybe one is sent to a left speaker, another to a right speaker. These are both functions of time, so we would call this this is an example of a signal. And again, we'll look at examples of waveforms coming up. Another example is that's a little different. This is a grayscale picture of a scene where you have two independent variables, one that corresponds to the x dimension and one that corresponds to the y dimension. And then the value of the function would be the grayscale intensity at a particular location in the image. Another example is a red, green, blue color picture of a scene. Again, we've got spatial dimensions, x and y, indexing our function as our independent variables, and then we have maybe three values for every pixel in the image, a red value, a green, and a blue value. And those combine together so that our eyes perceive color. Another example, getting a little more complicated here, would be a silent film. That's an older film. Maybe it's produced in grayscale, so you see a grayscale image or a grayscale video. There's no sound, but it's a function of both space and time. So the intensity that you see, the color intensity, the grayscale intensity that you see on the screen at a certain location, well, depends on the location that you're looking and on the time that you're looking. So there's three independent variables, x, y, and time, and then the value of the function takes on a grayscale intensity. Here are a few examples. I've chosen to start on the top left here with something called a hyperspectral image. This is a I don't know, maybe sometimes it's called an image cube, but basically there are three independent variables. Two of those variables are spatial variables, an x and a y variable, and then a third variable is a wavelength, usually denoted by lambda. So you've got x, y, and lambda being the coordinates or the independent variables, and that at each of those locations in the image, at every spatial position x, y, and at every wavelength, there is an intensity that's measured that corresponds to the amount of energy picked up by a sensor in that wavelength band that at that location. Another example is a synthetic aperture radar image. This is presented to us here as a grayscale image. So you have an x and a y dimension, and then the intensity is the amount of backscatter from different locations in the scene. In this case, you can see this is our nation's capital. Here you see the Capitol building, Library of Congress, the Supreme Court, and a few of the other legislative buildings over here on the side. Another example, again, this one is an MRI image, but you've got spatial dimensions. And in all of these examples, again, these are all examples of signals because we see that you have information being conveyed by patterns of variation in the image or in the waveform, the signal or the data cube, whatever it might be. So you have independent variables in each of these examples and then dependent variables. Here's an example of a speech waveform. So here we have one independent variable, which is time, And then the dependent variable is the amplitude of the speech signal at each time. And again, you can see and you can visualize when you're looking at the waveform the patterns of variation that are being presented here. It looks like what is being spoken is mining a year of speech. And people, linguists that are experts in speech, can look at the patterns of variation here without the labeling of the sounds and probably could tell you what this says even without seeing the labels or hearing it presented out of a speaker. Another example where we see patterns of variation conveying information is an electrocardiogram. And if you're a cardiologist, then you could look at this cardiogram and say, oh, okay, that looks like a healthy heart pattern. So once again, we have a signal is basically a function, or in discrete time, sometimes it's referred to as a sequence, but it's something that has independent variables and dependent variables. We will refer to the number of independent variables as the dimension of the signal, and the number of dependent variables as the number of channels or sensors or sensor channels in a signal. So again, coming back to some of the examples we've looked at earlier, if we had a monaural sound file, that's one-dimensional because we have one independent variable and it's a single channel signal. If you had stereo sound, again, it's a one-dimensional signal, and time is the independent variable here, so it's one dimension. But you have two channels. You have a left channel and a right channel. In a grayscale image, we would call this a two-dimensional signal because you have two independent variables, and then the grayscale intensity, that's just a single channel. For a color image, you'd have a two-dimensional signal, but it's a three-channel signal because you have at each XY position, you have three values, a red, green, and blue. For a silent grayscale video, that's a three-dimensional one-channel signal because you have three independent variables and one output variable. Now these variables, whether they're independent variables or dependent variables, could have different characteristics. If the independent variables are continuous, that could be continuous in time or continuous in space or wavelength, then we'll refer to that as a continuous time signal, with time in quotes here, because the independent variables may not represent time. They may represent some other physical quantities. On the other hand, the independent variables could take on values that are integers, in which case we would say that this is a discrete time signal. So for example, digital music is a discrete time signal. We would say that a digital image is a discrete time signal. Even though the independent variables represent spatial variables, we still refer to that as a discrete time. And there's a note here in the middle of this slide that basically says that the operations of sampling and reconstruction, which we'll talk about later in the course, provide an interface between these realms of continuous time signals and discrete time signals. If the dependent variables are continuous, we generally call that an analog signal, or a continuous signal. Or in the discrete, if the dependent variables are discrete, then we call it a digital signal. And there's some examples here that I won't go into. This is basically saying the same thing, summarizing what I just said. If the domain or the independent variables they can be either continuous or discrete, and likewise the range could also be continuous or discrete. We also note that the dependent variables could take on real values, like as a voltage in a circuit, or air pressure, temperature, whatever it might be, or they could be complex valued signals. And we'll see examples of both of those in this course. Another example is they could be finite signals, like they could take on symbolic values. A signal doesn't have to assume numeric values. Text is a signal, and the dependent variable in that case could be letters or characters or words. Signals are very general, our definition of a signal, and all of these things allow us to think about a very broad range of things as being signals. Here's an example of some of these concepts. So up here in the top, I have represented a waveform, a continuous time signal, continuous amplitude signal. And what I'm showing down below are samples of that signal. So what we've done is we've gone from a continuous time to discrete time. Now one of the, and notice that we've sampled this from time 0 up to about time 50. So in continuous time, the units have physical meaning, like in this case they may be seconds. But in discrete time, there's no real physical meaning to the units without associating it with the sampling rate. So the independent variable just has samples, units of just, there are no units really, it's just sample index. So, or it could actually take on some physical meaning like days in a year or seconds since January 1st, 1970. I guess it could also have some physical meaning as well. But the important thing to note here is that discrete time signals can be arranged in a table, whereas that would be impossible with a continuous time signal. There's just too many samples to represent. But a discrete time signal, you can arrange those values in order in a table, as you see here, for the first 50 samples of this discrete time signal. So again, continuous time, discrete time. Often when we're drawing discrete time signals, we'll draw them by connecting the points with straight lines, even though underneath we're really talking about discrete time signals. This kind of a plot here that you see is called a stem plot, where this signal up here, generally you would call this maybe a line plot or a curve plot. Discrete time signals are probably most appropriately represented by stem plots, but when there are many, many points, the stems all blend together, and sometimes it's more useful to just visualize it as by connecting the points in the signal by a straight line. So we'll see examples of both of those. Now, in this example, the values or the range that the samples can take on are real numbers, so they're continuous, even though they're shown here as numbers with so many digits of precision. Digital signals, we actually then will quantize those continuous amplitude values to a finite number of amplitudes using some number of bits to represent those values. And so again, this would be a true digital signal because we've quantized both in time and in amplitude. So here's a summary of the things we've talked about so far. A signal is something that conveys information in the patterns of variation. The dimension is the number of independent variables. The number of channels is the number of dependent variables. We can have continuous time and discrete time signals. And the amplitudes could be continuous or discrete, giving analog and digital signals. Let's look at some examples of signals. In all these examples, try to pay attention to how the patterns of variation in the waveform convey information. We'll look at examples involving sound, radio waves, as well as multidimensional signals such as images. The first example, even though I'm not showing here a picture of the waveform, this is the concept of sonar being presented. So you have maybe a surface vessel emitting a sound wave underwater that propagates, encounters objects which reflect some of that sound back toward the transmitter, and that can be picked up. And so by doing this sort of a thing, you can detect the presence of objects beneath the surface. fish or other objects. The same principle is used by bats as well as aquatic mammals to perform ranging and detection and tracking in their environments. Again, using sound waves. In the case of bats, it's high frequencies above human hearing generally. For dolphins, it's within the human auditory range. And then submarines use a principle called sonar. Here's an example of something that's common to us, speech. Again, you can see in the samples of the waveform here the patterns of variation. There's different kinds of patterns that you see here representing different sounds that we can hear, and different pitches and so on. What I've done in these other plots down below are zooming in on different pieces of the waveform. I can't remember what parts I'm zooming in on here, but now that we're in a little bit more close to the samples, you can see, oh, actually, yeah, it must be that just looking at the time axis here, which has been scaled to true time, I believe this is in seconds, you can see that we're looking at a zoom of this portion of the signal. And you can see an abrupt release of sound pressure here at the start, and then some noise-like signal followed by a periodic signal. And down below here I've zoomed in on this region from 2.5 to 2.55 so we can see up close this sort of a quasi-periodic-like structure that carries a lot of energy because the amplitude is high compared to these other pieces. What's actually taking place is sort of depicted over here. We have these vocal folds in our throat that acts like a buzzer, and our mouth and our nasal cavity acts like a resonant chamber where the sound emitted from this buzzer can resonate, and that produces sound emission from our body being projected out so that other people can hear and we can communicate. This is another way to visualize the speech waveform. Again, here we're making a plot in the time domain. Down here we're using a tool called the spectrogram. So the x-axis represents time and the y-axis represents frequency. And then you see the spectrogram itself is a signal, or is maybe another representation for the speech signal. Where you see black, that represents that that means that there's energy in the signal at these times and at these frequencies. And so what the spectrogram allows you to see is how energy moves in the waveform as a function both of time and of frequency. So you can see that these components of the speech waveform are shifting pitch, shifting frequency as a function of time. What's being spoken here is Bill Jones from Colorado. And you can see these different kinds of features. You have these voiced sounds like I and O in Bill and Jones. And then you see these other kinds of signals like F, the F sound, which has a lot of high frequency content, and so on. Another speech spectrogram example, again, time across this horizontal axis, frequency across the vertical axis. In this case, the person is speaking, "Children like strawberries." And again, you can see patterns of variation carrying the information, or the information being encoded in the patterns of variation in the speech waveform. Coming back to the dolphin example, we're looking here again at spectrograms, and you can see that dolphins, like humans, use chirps and just different whistling kinds of sounds to communicate and to perform their functions underwater. If you go to the Resources tab on the course website, you can actually download and listen to some of these audio examples. I have examples corresponding to dolphins. Here's another one with whales, a couple of different whale sounds. And then there's also a low frequency sonar that you can download and listen to. When you're listening to those, I'd encourage you to bring up these pictures and see if you can follow with your eyes the sounds that you hear with your ears. Again, on the x-axis you have time advancing from left to right and frequency going from low frequencies to high frequencies on the left. Another example that you'll find on the Resources tab is a music file. This is the first few seconds of a song that was popular a few years ago by Owl City. The title is Fireflies. But again, you can see that music is just a pattern of energy. It's just energy being carefully controlled and placed in the time frequency spectrum. And you can see down below here is the time domain waveform, and on the top you see the time frequency representation of music. If you knew what you were looking for, you could read the notes right off of this spectrogram plot. Again, I'd encourage you to listen to it, and as you listen to it, try and follow along with your eyes as the music transitions through these different notes and sounds. Bats use sound for navigation and for hunting. They have different, and they adapt their waveform based on the kind of activity they're involved in. If they're just navigating or hunting, they'll do different sorts of things. Again, human hearing goes up to about 20 kilohertz, so you can see that in most cases these bats use sound waves above human hearing. Radio waves are another rich example of signals. This picture really just shows propagation paths for radio waves as they encounter the ionosphere. A radio receiver takes a radio frequency signal. This could be a high frequency signal, maybe in the gigahertz or megahertz ranges, and using a sequence of signal processing operations, mixing, local oscillators, filters, and so on, you produce a low frequency signal. And generally there's two parts to this. There's what's called an in-phase piece and a quadrature piece. And down here below I have plotted the in-phase and quadrature parts for a linear frequency modulated pulse, LFM pulse. These are pulses that are used in sonar and in radar. This is an example of a signal whose dependent variable takes on complex values. If you think of the in-phase as being the real part and the quadrature being the imaginary part, we're plotting basically the real and imaginary parts of a complex signal here. And again, you can see that this is actually a frequency chirp if you were to listen to this, because we start from negative frequencies and transition to lower and lower negative frequencies, and then to DC, and then to low positive frequencies, and then to higher positive frequencies. So this is a frequency sweep through DC, from negative frequencies to positive frequencies through DC. You can tell the difference between negative frequencies and positive frequencies because for positive frequencies it looks like the in-phase part lags the quadrature part, and for negative frequencies the reverse is true. So the only difference really between positive and negative frequencies is that in one case sine leads cosine, that's positive frequencies, and for negative frequencies sine lags cosine. Again, here we're looking at the spectrum, the radio frequency spectrum, sort of an instantaneous plot here, and you can see that there's energy deposited at certain frequencies that represent radio broadcasts. And then down below is a spectrogram showing frequency across the x-axis and time running down the y-axis. So this is a common radio frequency display for like a software-defined radio scanner. Another example are biomedical signals. In this case, we have another ECG signal. I don't think I'll dwell on this too much other than to say that the patterns of variation that you see in the waveform correspond directly with physical anatomical things taking place inside the body. Here's one that's of interest to geologists, where if you have earthquakes and you place sensors or hydrophones over a distributed field, you're able to pick up the signals, and the patterns of variation that you see may indicate or convey information about the earthquake, the type of quake, the magnitude of the quake, and so on, and would also allow you to tell when the tremor or the measurement was not actually produced by an earthquake at all, but rather by a nuclear test, for example. Here's a two-dimensional signal, an image, in this case a grayscale image. And again, what I'm trying to do is come back to this idea, the theme here, which is that a signal conveys information by the patterns of variation. If we were to take this signal, for example, the picture of this boy's face, and slice it right across where you see the red line drawn, and then take those pixel intensities and draw them as a line plot, what you would get is the line plot shown below. So notice that where the image is dark, you have low intensity on either side of this boy's face. But then in the middle, where you see the boy's face, that's lighter intensity here, and so we see these intensity values peaking up as we move across the portions of the face, and we encounter shadow on the side of the nose, and then maybe a glare as we move across other parts of the face, encounter the ear, and then step off back into the background, which has lower intensity. Contrast that with an image that's basically a nonsense image, a white noise image, you might say. If we slice that image at the same location and then make a line plot, it's difficult to see that there's really any structure at all. There may actually be structure here. Without doing additional analysis, we don't know. But the point is that, again, the patterns of variation that you see convey information. Here's another example with a color image. Remember that a color image is produced by 3 channels, a red channel, green, and blue channels, and you put those together and we perceive it as color. So this is a 2-dimensional image, but a 3-channel image. And again, the patterns of variation build up or contribute to something that is pleasing. The other thing that we can deduce by zooming in and taking a close look at this image is that it's a discrete time image, because if you zoom in far enough, over here on the right I'm zoomed way in, we can see that it's not a continuous spatially sampled image. It's actually sampled at discrete points, and when we zoom in this far we can actually see those individual discrete pixels. So we would call this a discrete time image. If we took a look at the numeric values of the red, green, and blue channels, we would also see that there's, I'm guessing in this case, 8 bits per pixel per color channel. So there's 24 bits if you total up the red, green, and blue, add all those bits together. So every pixel here is represented by 24 bits of information. So it's not a continuous amplitude image either. It's quantized, it's digitized. Here we are back to the hyperspectral image example. So remember, this is a 3-channel image. We have an X coordinate, a Y coordinate, and moving back a lambda or wavelength coordinate. And then at each of those locations we have a value that represents the amount of energy picked up by the sensor coming from that XY direction and in that particular wavelength band. There's a few slides here that talk about how hyperspectral images are generated, and I'll pass over those. But it's interesting, and there's much more that you can read about online. Here's a few other examples before we leave the concept of a discrete time signal. The daily closing stock price. This is automatically a discrete time signal. It's sampled once per day. And the patterns here are of great interest to people in finance and to investors. In this case, you see NVIDIA Corporation. Their stock price has risen over time, so that's interesting. Another example of a discrete time signal, or of a signal, is music. In this case, the dependent variable, the independent variable is time, and the dependent variable is quantized to notes that are played by each instrument. So I would call this a discrete amplitude signal. Another example is text. In this case, the values of the signal are actually symbols. You could think of it either as letters, words, punctuation, whatever the case may be. But it's a one-dimensional signal. We read from left to right and down the page as if it was one long string of characters, and then the characters themselves are the values of the signal. And the number of examples goes on and on and on. Recorded music, whether it comes from an audio tape, which maybe you could think of as a continuous time signal, and if you compared that to a modern compact disc music, the data here on the compact disc is stored as bits. So this would be a discrete time signal. But we perceive it when it's played back as a continuous time signal because it's processed through a digital to analog converter before being sent to the speakers. In these examples, I hope that I've been able to communicate the concept of the definition of a signal, the dimension of a signal, the number of channels of a signal, helped you to appreciate that this very general definition of a signal, that a signal is anything that conveys information through the patterns of variations in the waveform.